My name is David Foreman, and I'm with Design Profit, and I will be giving a brief overview on the Design Profit software, some of the methodology and the symbology. And then Maggie, who is our senior statistician, will step the participants through how we develop cost models using the Design Profit framework. And then Andrew Cordoni, one of our senior developers, will then show you how we're using our custom math apps and custom fields to generate the algorithms that drive the cost modeling. And then we'll leave it open for some questions. So the first thing I'd like to do is basically give you an overview of our platform and how it is that we use this to develop cost models. Munro Associates is our consulting arm. Design Profit is the platform. So we take our costing knowledge and data that we've collected over the last 30 years in process, machining, tool, labor, and other costs, and we push that into Excel cost sheets where we've developed cost applications. That is very similar to what a lot of our customers are currently doing out there today with their costing, is a lot of their knowledge base is sitting in Excel. So what we want to do is we want to take our Excel cost sheets along with our material library, which has piece costs as well as material properties, and drive that into custom fields and algorithms. We then, once we have all of that information translated, we then model our costing using Design Profit. With that, we can also look at all the different options. So as we go in and we look at metal stamping or injection molding, we can look at all the different options as we select, and Maggie's going to show you a little bit about that. So once we use our software to develop these different cost models, they become a integrated piece of the software, which will provide consistency within the organization. So now I'm going to go directly into our software so you can take a look at our software. So the example that I'm showing you today, since this is a heavy industry conference, is a tractor, and it's really focusing on the combine. I can't get into too many specifics on who the customer is, but what we did here is we did a benchmark study between two different organizations and then developed different ideas, and then we combined those ideas into a redesign. So Design Profit uses symbology to model the design and the manufacturing process, including all the tools and operations that you need to do the job. So you'll see symbols at the top of the software. So that represents parts, sub-assemblies, pre-processed parts, your tools that you need to build it, whether it's a fixture, whether it's a hand screwdriver, power screwdriver, or whether it's an actual stamping press. And then fastening is how do you actually fasten, whether you're screwing a part in, you're welding it, or gross deformation. And then all of your secondary operations, your machining process inspections, and then options, so that if we have more than one way to do the job, or we have more than one option like seat color or other implements. And then parallel activities where we can model multiple operators working within the same cell. And then we have a way to actually model work cells, so we can look at what the actual roll-up costs are for a work cell. It's a drag and drop interface. You just drag and drop your part, and then you can enter your part number. If it's in the library, it'll automatically pull that information in so that you have your costs and all your other information in it. So this happens to be a clamp. We can also import all this information directly from a tab delimited format as well. So once we have modeled a complete product like this combine, we can then go in and then model a competitor vehicle as well, so that we can understand what the cost and complexity of a competitive vehicle is. Once we have these modeled, we can create an executive summary. With the executive summary, we can take a look at how many parts does Tractor A have, how many parts does Tractor B have, how many steps, actual time, how many fasteners, and a bunch of information. We cannot provide the cost for Tractor A because of some agreements, but Tractor B is, you can see, is $298,000 is how much we've modeled and rolled up through the model. And we look at what the total labor cost is, quality cost, and then what the total cost is. Once we have this information, the next thing that we want to do is we want to come up with ideas. So we start our ideation phase, and we start to capture each one of those different ideas. We can then take those ideas and actually assign those to a redesign. Once we do that, then we go into our redesign and we start to model what parts are new and then what parts are going to be deleted and replaced. We do the same thing then with our level 2 blended, which is blending some low innovation ideas with high level ideas. So we're blending our risk. Once we do that, then we can rerun our executive summary. And the executive summary then is taking our Tractor B and then looking at our level 1 and our level 2 blended and what percentage improvement that we're seeing. So here we're seeing a 28% reduction in parts, a 37% reduction in our steps, and our producibility score is improved by 35%, which means that we can build it a lot easier and a lot simpler. Reduction in fasteners and our fastening operations, as well as how many times that we can assemble the product wrong, our weight, and so forth. So when we look at it, we get down to what our total cost is. And we see here that on a low risk redesign, we can improve it by 10%. If we want to introduce a little bit more engineering, a little bit more risk, we can reduce our cost by 18%. And we can see here where our annual savings are. So this gives us a way to very easily, very quickly model our baseline, also do benchmarking to look at our ideas and come up with a good business case that drives us in the right direction and reduces our risk. So with this, what I'm going to do is show you how we take this exact same system and drive this into an ability to actually generate cost models that can be used within your organization. And at that point, Maggie will give you an overview of that.
Okay, thanks, Dave. Hi, I'm Maggie. In the following portion, I will show you our new costing product, ClitoCost. How do we estimate the costing and create assembly maps by using ClitoCost? First, I will show you the injection molding process. Here in Design Profit, we need to create a pre-processed part. We just simply click and drag into the window. I have already created the pre-processed symbol, so I can show you. After double-click the symbol, we can see here we can enter the number, name, description for the part information. We also need to enter the weight for the part, the material of the part, then click OK. This is a basic symbol for this part. This symbol represents a part of B-pillar lower trim. We right-click the symbol and click the cost. Then we can see this screen. First, we need to choose a cost model. We have some different models. For this particular part, we need to choose plastic molding. Here, for the process, we need to choose the injection molding process. There are many questions we need to know for the costing estimation. First is a part efficiency percent. The default is a 100%. Then is a run quantity. The run quantity is a complete number assembled before the factory ceased production in that batch. The question is for the material cost per pound. Basically, the number is put out of our material database. The next question is about the changeover. User can choose no changeover or single minute exchange die or manually change over. Dimension unit here is for the unit of measurement, which will apply to all the following questions regarding the length, distance, and so on. Here we choose a millimeter. The next is regarding part coughing dimension. Part coughing length, part coughing width, part coughing height. Users can measure the part and enter those data here. This is about the part average wall thickness. The same, we can measure the dimension and put here. Next question is about the cavities. How many cavities or parts in the die? If the part has dialog features, we can add information here. For this particular part, BP latrine, it has 7 dialog features. This geometric feature will require some extra action time for the process. The next question is about the safety tonnage. How many additional percentage of tonnage is required to protect the machine? Here we use default 10% of a safety tonnage to protect the press. Here users have the option to choose whether the injection molding process needs a chiller or not for the cooling purpose. Next question is about the projected area percentage. This percentage is the part two-dimensional surface area projected onto the mold. The following questions are about the runner system, which are the channels within the mold and sometimes require extra material. There are 3 options, cold runner, hot runner, and direct screw. If the part is made by the cold runner, there are some other questions we need to identify, like area increased percentage, weight percentage increased. By default, it's a 5%. However, people can override. User can choose whether the process needs a regram or not. The following question about insert. Sometimes injection molding process requires an insert to be set inside a mold before the shot is injected. How user want to load, manually load one by one, or manually load multiple inserts, or just by using robots. This question is regarding the foaming agent. A foaming agent is a substance to create a foaming structure within the plastic, often for weight reduction. We need to know some information. The type is gas or pellets. What's the volume? Next option is hollow core. Using hollow core can decrease the amount of required material, decrease weight. What's the type of hollow core? Gas assisted or water assisted hollow core? What's a reduced short volume percentage? The next question about the colorant. Colorant may be added to the material to control the color of a part. The following types of colorant may be selected. Users can select liquid colorant or pellet colorant. If using coloring enters the percentage of colorant by weight to the shot. If a part is made up of more than one material or different colors, then it may require multiple shots into the mold. For a multiple shot molded part, the information on the main shot must be entered first, and then the information needed to be re-entered for the second and third shot. An option for multiple shots is that they are simultaneously or sequential. For the second shot, all the questions are similar to the main shot. Second shot may require different selections or inputs. It's the same for the third shot. There are similar questions to the main shot. Users can input different settings here for the second and third shot. The last question about the unloading parts includes the unload method and whether or not a conveyor will be used. For the unload method, the following selections are available: can drop out the part, or manually unload, or use a robot to unload. Then we finished all the inputs and just click OK. Now we can see those symbols and assembly have automatically generated. This includes machines. What kind of machines need to be used for this process? This is a cycle per part. It contains the whole cycle of the injection molding process. The part of the B-pillar train only needs one shot, so there is only main shot information. This is a part symbol representing the main shot material. This is a material modification symbol representing injection molding process. Here we can see the number inside the symbol. It means how many seconds will be used for the injection molding process. The operation symbol represents a method to unload the part. Here we can see a green color note. When we click here, we can see it contains very detailed information about the process and the costing. It's a date, the time, when we did the critical cost estimation, the part information, the part dimension, the process information about the injection molding, cycle time, about the main shot. Just now I showed you critical cost injection molding model. We also have some other critical cost models regarding metal stamping processes. I will give you a brief overview about the critical cost metal stamping transfer line model. The interface is very similar with the injection molding critical cost model. I will use a fender as an example to demonstrate the costing information. Right-click and on the pre-processed symbol and click cost. For this part, we choose metal stamping for the model. The process, we select the transfer line stamping. We can see here there are many different questions regarding the transfer line stamping process. Like the run quantity, how many parts can be produced in one run, the material cost per pound, the dimension information. We separate the blanking and shearing process from transfer line process. So if the users want to cost the blanking and shearing process, they can select the option about the changeover. This is a place user can enter the blanking length for the process. For transfer line metal stamping, our model has the capability to map as many as 16 stations. For this part, fender, we need 4 stations. We can enter different operation information for each station. Then after that, we can choose whether the process needs a changeover or not. The transfer method, how to transfer part. The last question is how to unload part. So after entering all the information, we click OK. Then the estimation note and the costing diagram will be immediately generated, like the injection molding. This is an overview about the click-cost metal stamping transfer line model. We also have the costing model for progressive die and the transfer die. They work as similar as the injection molding and the transfer line model. This is a part of our click-cost models. In next portion, Andrew will show you how to use customer fields to develop the click-cost models.
Thank you, Maggie. Hi, my name is Andrew Cardone. I'm a senior developer at Design Profit. And what I want to focus on here are the results that we're generating with the click-to-cost model and how we actually used our formulas and our custom field system to not only define the calculations that were used to generate the material costs, the machine costs, and labor costs, but also the various formulas that we use to select machinery and whatnot. I'm going to focus on the plastic injection molding examples that Maggie showed for us. And as we're looking at this particular model that we were just looking at, we noticed that in this model we have machine center. The symbol collects together a set of machines. Using our formulas, we have conditions that we predefine that indicate the tonnage that's required, and we automatically select a machine. And in addition to that, we select all the auxiliary equipment that goes along with this. Now, in constructing cost models, this was one of our design goals. We wanted to not only capture labor costs and material costs, but we want to take it a step further and assign a machine cost to a given process and all the various options that you may have selected on here. So you can see in this case, we've included things like TCUs, robotics that are there. And what I want to show you, what I want to focus on first is, to get this machine cost, we first had to answer a fundamental question, and that was, how much does 1 hour of a machine cost? Now, at Munro, we've had to answer this question before, so we've developed formulas that answer this question. So in this case, we see this actually costs $45.29. Now, we were able to use our formula system to actually embed this intelligence into our application, taking it out of Excel and putting it into a location where not only it can be kept in sync with all our projects, but it can actually be better defined, and it's a bit more readable now than it was in its original format. So as we go in here, I'm going to give you a quick overview with what we're looking at, which is our custom field definition screen. What we see here are custom fields. Custom fields can either store information, that is entered values, or they can contain formulas, much like the syntax of formulas one would find in Excel, and a little bit more. We organize those fields into groups. Think of these as libraries or packages. These groups can contain other groups within them, and so on and so forth. And we use these fields in order to not only drive the calculations, but also make selections on which machines, calculating material and whatnot. I'm going to go into the group that defines the machine burden. So the field we were just looking at actually comes from this field labeled calculated machine cost per hour. So in Excel, you would typically have a cell that would have this as a column header and would have a sequence of functions and whatnot. But one of the things you're really missing in Excel is you really don't have any comments or explanation of why things are happening. So in this case, this is the first thing I'm going to point out from our formula system. We can actually comment and explain why we're doing things. And it makes it a lot easier for us to track changes, for us to look at something a year later and find out, well, why did we do this? And in addition to that, we also use named variables. That is, our fields, instead of just being cell references, like A3 or whatnot, we actually give them names. Notice that they're delimited with square brackets, and this allows you to do different things. One is to actually have embedded spaces. But in addition to that, our application is ready for internationalization. One could put Spanish in here with letters like A, or any character set that you like. Now, the simple equation tells us how we take the variable and the fixed expenses, and we get that. those in turn are defined further down. You can see that we actually build up our variable expenses through all the various utilities that we use up. In this case, this machine uses electrical energy, natural, so on and so forth. That's one level of functionality that custom fields can provide. Now, we mentioned also that we were able to calculate and determine which machine we wanted to use. Specifically, we selected a press that required a certain tonnage. Now, within our custom fields, we also capture that. We actually have a group here that's labeled plastic molding. And within this, we have a group within it as well labeled injection molding. Within here, we actually have calculations that specifically tell us what the required tonnage is. So what this lets us do is we define fields that contain formulas and functions that specifically will calculate the minimum required tonnage. And they're all labeled in such a way that we can easily find them. They're grouped much like a folder system, making it a lot easier for us to manage this versus having it spread throughout various sheets in an Excel spreadsheet. And as I expand this in here, this actually not only captures just an expression, you know, that we would have in Excel, but rather this actually defines a function that can take inputs, that is parameters, arguments, and return back a value. So I'm going to use this to also highlight some of the differences between our formula system and what one would find in Excel. We initially started trying to model our formula language like Excel. Basically, it's the most used programming language in the world. However, it has quite a few limitations. I've already mentioned comments. But the other one is that you're putting everything into a single expression. I think many people are familiar with clicking on a cell and seeing a formula that's so complex because of and function, or functions, and if functions that you're not really sure what you're looking at. Couple that with the fact that typically people don't name their cells. You're going to have something that is extremely difficult to understand and to maintain. Well, what we did to get around that is we applied basic programming standards. That is, we have statements. So in this case, I have inputs. I can define variables such as base tonnage, and I can define a series of them, and it all works up to a final calculation on how much force is required. Another thing that our system has, which we make use of in the formula here, is that we have a notion of values with units. So not only can we say something is a numeric value, and we're going to return that, we can actually attach a unit to it. So in this case, I'm saying that this is in fact a value of force with short tons as its unit. We have the same thing for time. We have the same thing for weight. And we have many other measurement dimensions that we allow you to model in this application. It's very important because there's quite a few examples of issues with calculating values, say in English unit system, and converting it back to metric and so on and so forth. So you see in this case, we stuck with PSI, inches. It's very clear that's what we were doing. In fact, the variable name indicates that, predicted area in inches squared. In addition to that, you can start building up much more complicated data. That is, you can create data structures that you can begin collecting together and returning to make decisions. So when we built this, rather than having a disjoint set of calculations, we actually decided to use something that looked a bit more like an object, in this case. I'll show you right here. So we collected together into an object that we called our entered information, which includes calculated values and whatnot. So let's scroll down, pardon me. We collect all these calculations, and really it's the result that matters here. But what we have here is basically an object that has a name-value pair set of properties or fields and values. So we actually define and record all in one place part information. The inputs on the part, width, height, and so on and so forth. And not only that, but we also record the tonnage that was required, a lot of the intermediary values that we calculated during the cost modeling, such as the injection rate, mold travel distance, so on and so forth, information on the specific shots, all put together here. So what this allows you to do is in one place, make all your calculations, collect it together, and then you can do something like the note that we have here. As you can see here, this basically indicates all the information that we collected together. And we're automatically generating the rich text that defines the formatting on this. It's all done programmatically for our formulas. Makes it extremely flexible We could export this to HTML, what have you. It doesn't matter because we're generating it using our formulas. So there's an awful lot of flexibility there. In addition to that, throughout the system, whenever we need to do something dynamic, such as select a symbol or perhaps calculate formatting on the color on a report or what have you, we can actually use our formulas. So in the model that was used to define this process that we have here, which is labeled under the cost models, we've actually embedded the usage of these formulas here. So we've modeled all the various options, and you can see, recognize some of these from the inputs that one put in. We actually have an output, it's hidden, and it dynamically generates the output that we have on the screen. So in this case here, we've collected together the machines. We need to select a press, and we can use a formula that we defined here to get the entered information, and then iterate through every symbol in the list that represents the various possible presses, filtering by the tonnage, and get the first one that meets our requirements. And if we don't happen to find one, then we can indicate to you, make it obvious that we're not able to find a press. In addition to that, you can see that we have various other pieces of equipment that can be dynamically included or not included, depending on the information that was entered or calculated. So this gives us quite an advantage in terms of being able to model exactly what's required in a process versus just making assumptions that in general people use this size press, or in general we always have a TCU. We can get as precise as you actually need to make your estimate using the system.
Thank you, Andrew.
Right. Thank you.
So one of the things that we're providing to our users through the Design Profit platform is a standardized and repeatable process for integrating and modeling multiple cost and knowledge sources so that we can implement a system within an organization that everyone can easily use. So I thank you for taking the time out of your schedule to be part of this webinar, and we'll open it up for any questions that you might have.
Okay, thank you very much. If you do have any questions, please feel free to use the QA or chat boxes. I'll go ahead and release the rest of the poll questions while you might be typing. And first one is, how would you rate the content of this webinar? Okay, thank you. Next one is, would you like additional information about Design Profit? Okay, and then finally, would you like any additional information about the Altair Partner Alliance? All right, thank you very much. We'll give it a few more moments in case there's any questions that are coming in. But I do have a recording of this webinar, and I'll send a link to everybody afterwards, as well as the slides that everyone was presenting. So, all right. If there are any questions, I'm going to send a recap email, and I'll include Dave's email address so that you can have any questions filtered through him. But at this time, I think we'll go ahead and end the presentation. Thank you, everyone, for attending today, and thank you to all of our presenters. Have a nice day. Thank you.